Let us start our review for the subject reinforced concrete design. Situation 1, a rectangular beam has a dimension of B equals 250 millimeter, H equals 650 millimeter, and D equals 600 millimeter, and is reinforced with 325 millimeter bars. Use FC prime equals 28 megapascal and Fy equals 420 megapascal. What is the cracking moment of the beam? We analyzed a reinforced concrete beam using two ways. First is the elastic method. So meaning we will consider the composition of concrete and steel as an elastic material. So we will use the principles in strength of materials in analyzing it. And then the other way is we will use the ultimate strength design. So meaning we will base the analysis of the reinforced concrete based on limit states of the concrete and steel. For the question, cracking moment of the beam, the process in determining the cracking moment of the beam is using the elastic method. So meaning we're just using the principles of strength of materials. So first, we have to determine what is the value of the stress that will cause the cracking of the beam. We call that as the modulus of rupture. And based on the code equation for the modulus of rupture is 0.62 lambda square root of Fc prime. So we substitute our given values. So our lambda, that is 1.0 for normal weight concrete. So if it is not indicated in the problem, if the concrete is normal weight or not, so we always assume that it is a normal weight concrete. Therefore, the lambda value corresponds to a value of 1.0. And then for the FC prime, so we call this as the 28-day compressive strength of the concrete. So when we say 28-day compressive strength, so this is the strength that is achieved by the concrete after 28 days. So we substitute the value 0.62 times 1.0 times the square root of 28. So the value of modulus of rupture is 3.280731626 megapascal. Okay, so this is now the stress that will cause the beam to crack. So in order to determine the cracking moment, so we will use our formula in strength of materials, specifically the formula for flexural stress. So the formula for flexural stress is simply MC over I. Okay, so we substitute. If we are computing for the cracking moment, so meaning the flexural stress will reach the modulus of rupture. So the computed value of 3.28, we substitute here. And then we substitute C and the moment of inertia. So take note, this is just a rectangle. So for its moment of inertia, we just compute the moment of inertia of gross area of the rectangle without considering the effect of the steel. So that is 1 over 12 BH cubed. And then C, this is the distance from the neutral axis towards the farthest fiber. So if it is a rectangle, so from the neutral axis up to the fiber, so that is simply 650 over 2. We can now solve the MCR, and that is 57,754,546.33 Newton millimeter. So in kilonewton meter, that is 57.754,546 kilonewton meter. Okay? And that is letter D. Next. Determine the uncrack transform moment of inertia of the section. So naturally, if concrete is subjected to extreme tensile stresses, so it will start to crack. So if we are asked to determine the uncrack transform moment of inertia, so meaning this is the stage wherein the concrete under tension is not yet cracked. Okay, so that is why it is called uncrack transform moment of inertia. Okay, so for example, here's our beam, and then the reinforcement is placed at the bottom. So meaning we are assuming that the tension is at the bottom, and then the upper side is subjected to compression. So when we say uncracked transform moment of inertia, we consider that the whole concrete is not yet cracked. So meaning in computing the moment of inertia, we will still consider all the area of the concrete. But this time, we will be more precise or accurate in determining the moment of inertia. So meaning, the portion of the concrete occupied by the steel will be considered already. Previously, we have not considered the effect of placing the steel in place of the concrete. But in determining the uncrack transform moment of inertia, so we will start to consider the effect of placing the steel in replacement of the concrete. So we have D. D is what we call the effective depth. So when we say effective depth, that is the distance from the centroid of the steel reinforcements to the extreme fiber in compression. Okay, and then we have H as the symbol for the overall depth of the concrete. These are the standard symbols used in the reinforced concrete design for rectangular beams. So we have to locate first the neutral axis. Previously, we have easily located the neutral axis because we only consider the section as a rectangle with complete concrete. So meaning automatically the neutral axis will fall at the center of the rectangle. But this time, since we are already considering the effect of the steel, the neutral axis will not fall at the centroid of the rectangle. So we have to locate first the neutral axis because we already have steel reinforcements. And take note, steel and concrete are two different materials. So therefore, they have different modulus of elasticity. So let's say the distance of the neutral axis is at a distance of y sub t from the top. So let's start. When locating for the neutral axis, we have to equate moments at the neutral axis. Okay, so from the definition of the neutral axis, the moment of the sections above the neutral axis with respect to the neutral axis should be equal to the moments of the elements below. They should have equal moments. Okay, so how are we going to represent that? This is the equation. So take note, this is not a general equation. So meaning you don't need to memorize this because you can simply derive this based on the dimensions given. First, the portion of the cross-section above the neutral axis is simply a rectangle. This is just a rectangle. So we take the moment of this rectangle towards the neutral axis. So the area is B times Y sub T. And then we take the moment of that towards the neutral axis. That is, we multiply it by Y sub T over 2. Because it is a rectangle, so the distance of its centroid is at a distance of Y sub T over 2 from the neutral axis. And then, we take the moment of the elements of the cross sections that are at the bottom of the neutral axis. So first, we take the moment of the rectangular part. So that is B times H minus Y sub T. So how do I get the H minus Y sub T? So H minus Y sub T, that is the height of the rectangular portion below the neutral axis. So B times H minus Y sub T times H minus Y sub T over 2. So that is the moment of this rectangle. Then we take the moment of the steel reinforcement. So A sub S times D minus Y sub T. A sub S is the area of the steel and then we take the moment of that towards the neutral axis. So how far is the centroid of this steel reinforcement towards the neutral axis? That is D minus Y sub T. And then we have here N, which is called the modular ratio. So we use modular ratio because steel and concrete are two different materials. We multiply the area of the steel reinforcement by N because it is stronger than the concrete. So later on, we will compute the value of this N. And then, take note that if this is already steel, as you can see in our first term on the right side of the equation, we have considered that the area of the concrete is whole, while in fact, if we have placed the steel reinforcement here, there is a part of the concrete that is displaced. So that is why we need to subtract again the area of the concrete that was displaced. Of course, that area is also equal to AS. And then we multiply it by its moment arm d minus y sub t. Let us simplify first this term. So take note, there is a common term, as and d minus y sub t. So if we factor out as and d minus y sub t, so we will obtain as times d minus y sub t times n minus 1. Okay, so we can now substitute the values. The value of the width is 250, H is 650, and then AS, according to the problem, the beam is reinforced with three 25 millimeter diameter bars. And then we need to compute now for N so that we can complete this equation. Okay, so how do we compute N? So in general, the modular ratio is simply determined by taking the ratio of the modulus of elasticity of the two materials involved. So that is the modulus of elasticity of the stronger material divided by the modulus of elasticity of the weaker material. So in this case, our stronger material is the steel. So its modulus of elasticity is 200,000 megapascal. We divide it by the modulus of elasticity of concrete, which is 4,700 square root of Fc prime. So our Fc prime is 28. So we substitute 8.04179728. Okay, so we can now substitute N in our previous equation. So we can now solve for the value of Y. Y sub T equals 341.4963.45 millimeter. T, we can now compute for the moment of inertia. For the moment of inertia, take note, this is our location of the neutral axis. So we will transfer all the moment of inertia towards this neutral axis. So first is, let's say, the moment of inertia of the whole rectangle. It would be easier if we consider this rectangle as a whole. So that is 1 over 12 BH cubed. But take note, its centroid does not coincide with the neutral axis. So that is why we need to transfer its moment of inertia. So we need to add area d squared. Okay? So area is simply b times h, and then d squared is the distance of the centroid of this rectangle towards the neutral axis. That is y sub t minus h over 2 and then squared. So this is the for the concrete part, and then for the steel part, that is AS times n minus 1. Recall that we have here minus 1 because we need to subtract the effect of the displaced concrete times d minus y sub t squared. So actually, the centroidal moment of inertia of the reinforcement were neglected already. So take note, for the moment of inertia of circle, we have pi over 4 r to the fourth. But for computation in reinforced concrete design, the moment of inertia of the steel reinforcements, pi over 4 r to the fourth, are always neglected because their effect is very minimal. So that is why we no longer include that in the equation of the moment of inertia. Okay, so we substitute the values. So we have moment of inertia equals 645,585,3500. Okay, next. Calculate the stress in steel reinforcement caused by a bending moment of 55 kilonewton meter. Okay, so ika-calculate naman natin yung stress. Ibig sabihin, kung magka-calculate tayo ng stress and then the given load is a moment, so meaning, again, we are using the formula for flexural stress. So here's our section. So in determining the flexural stress, that is simply MC over I. So we have modified this, but of course, the principle is still there, MC over I. So when we say C, that is the distance from the neutral axis towards the point where you are computing the stress. So in this case, we are computing the stress in steel. So how far is steel from the neutral axis? So that is D minus Y sub T. D minus Y sub T. That is the distance from the steel reinforcement towards the neutral axis. And then, moment of inertia. The computed moment of inertia is in terms of concrete. So since we are computing the stress in steel, so we need to convert this moment of inertia into steel. That is why we are dividing the moment of inertia by the modular ratio. Okay, so that is 645 divided by 8.0. That is 17.70 megapascal. Next, calculate the compressive stress in the concrete caused by a bending moment of 55 kilonewton meter. So compressive stress naman in the concrete. So here's our beam. So again, we will use the formula for flexural stress, mc over I. But this time, we are computing for the stress in the concrete. So how far from the neutral axis is the concrete fiber in compression? So of course, this is the concrete in tension, and then this is the concrete in compression. The distance is y sub t from neutral axis up to this point. So that is why my over I. We don't need to divide by modular ratio because we are computing the stress in concrete and our moment of inertia is in terms of concrete. So that is why here's our value. Okay, so please compute for the stress in concrete 2.908 megapascal.